Good afternoon. Welcome to Krishna's classroom. Now, before we take up the boundedness and continuity of linear transformations, let me just make a remark on what I said last time. This is just something which is probably clear to you that we considered this, that is x equal to R2 and a vector space over R. On that, we defined this is equal to x equal to, and we have this for 1 less than or equal to p less than infinity, and in this case we have seen that this is a Banach space. For each value of p. In fact, for p equal to 2, we have this is the Euclidean norm, and this is derived from the following: the inner product this is how the inner product is defined, and when x equal to y, you get norm of this is what we have. Okay. So this is the norm is derived from the inner product. Now in this case, the unit circle is a perfect circle symmetric about the origin. In all other cases, this perfect symmetry is not there. It is symmetric, although, but it's not a perfectly symmetric about the center. I hope you catch the point. Okay. Now let me. So that is the remark I wanted to make. I thought it's better to add that. Otherwise, it may be. Although it's all clear to each one of them. Okay. Now we come to the theme of today's lecture. This is about boundedness and continuity of linear transformations. So let given an attributed a norm in very many ways. I mean that's already fixed. So it is well fixed in the beginning itself. Now we define the following. So let linear map. That means lambda of x1 plus x2 equal to lambda x1 plus lambda x2. Lambda of alpha x1 equal to alpha times lambda x1. Okay, right? So that is these two conditions are satisfied by for every x1, x2 belonging to x and alpha belonging to the field. This is what we call the linear transformation. Now we shall take f to be C, or that means our consideration will be real vector spaces or complex vector spaces. I mean, we work on that. Now we define then only all these definitions will be define norm lambda to be supremum of norm of lambda x, norm of x for over the supremum taken over now. One remark I want to make is this, that the norm lambda x, see, lambda x belongs to y, is with the norm in y. So if you want to make this explicit, you can do one thing. You can take x with norm x, and see, you have this scenario. You take x distinguished by which we mean that these two, the definition of these two could be quite different. Okay. So in that case, we will be talking about this one, norm of y here. So it is, we are using the norm, definition of the norm in the x space, and the other one y space. Now you see, both are assumed to be vector spaces over C or R. Okay. So what you do is you take lambda x and take its norm in y and compute its supremum over the unit ball in x space. Okay, that is taken as, and that is the norm. Okay, now one can show that. Norm okay. That means norm of, see, you are looking at Lxy is set of all lambda, where lambda is a map. This notation is not absolutely proper, so let me just write here, because I want to use this, reserve this for a situation where it is on. So let me designate this by, say, let me designate this by, sorry, it says uh, okay. So M consists of all linear maps from X2. Now we define, what we have defined is the norm for that. If the supremum is finite, then you say it's a bounded transformation. So for every element of M, you can define something like this, and in general, this could be unbounded also, right? Now, if norm then